welcome back. I'm going to continue with the discrete logarithm theme. And I want to switch gears a little bit though. I want to talk about a quantum programming language. It's basically a bit of a shameless self-advertisement. It's something I'm working on together with others at Microsoft Research. And I want to highlight that there's a language that you can all use, you can access it, and I wanted to highlight that you can even use it to implement something like a VLOG algorithm, at least like for very small scale problems. So that language is called Liquid, and it's basically a programming language, but also a simulator. And it's based on a .NET language, so Microsoft has this .NET framework. One of the Microsoft languages is called F#. It's a functional programming language. And Liquid is implemented in F#, but basically it's an embedded language into F#. It interfaces to a bunch of simulators. So there's a universal simulator that can simulate any quantum algorithm, but there's special purpose simulators if you know a bit more about your circuit. And there's the various runtimes. You can simulate it as a client, but also as a cloud service. You can, from your language, once you express the algorithm, you can then generate circuits, and you can further optimize them using rewrite rules. Oftentimes you can cancel stuff. You can equip your circuits with error correction. You can simulate basic noise models in that framework. And long term, and this stuff is kind of for the future, that's something our group wants to implement in the long term, is to interface it with actual quantum computer hardware. So we could drive the hardware using the programs we implement in Liquid. And then they would map to backends. There could be a classical backend, quantum backend hybrid systems where they're quantum and classical at the same time. At the moment, one of the kind of nice things and main applications maybe even is that you can render circuits. Once expressed in an algorithm at a circuit level, you can not only simulate it but just export it, say, into a PDF or an SVG format. It's very nice if you write papers to be able to do that. It's just like a small application, but at the moment I find that it's incredibly useful. There's a paper if you want to check that out by Christos Ore and Dave Wecker. Dave is our main architect of that Liquid system. Okay, and so it is available publicly. You can download it from GitHub. A few examples are there. There's a manual, and I recommend to use that. There are other competitors, I should say. To be fair, there are other programming languages. Notably, there's a language called Quipper, which is also a functional programming language. It's implemented in a different host language. They use Haskell for it. In terms of simulation capabilities, you might find Liquid more useful, but certainly also Quipper has its benefits. A simple program would look like this. So if you want to express, for instance, teleportation, that's sort of the quantum version of Hello World, you could do it like this. So this little program here, EPR, stands for EPR pair, would correspond to this circuit. And what you would do is you would give it a set of qubits. The let is a functional keyword in many functional languages, like OCaml or ML, you have the let keyword. It's like an assignment. And here you define a function that, you define a function that takes one argument. QS is a register of qubits. And what it does then is it applies a Hadamard to the first element of the list. So QS is a list of qubits. It applies a Hadamard to the first element of that list of qubits, and then a C0 to the first two elements of the list. So you see then in the circuit on the right is a Hadamard followed by C0, and it's rendered automatically if you choose to output it into a circuit. And the entire teleport algorithm would look like this down here. So you give it, again, a list of qubits. In that case, it would be 3. You define a sub-list of the list, namely you define a sub-list, namely the tail. So you crop everything except for the head. And then on the tail, you first call that function that we defined up there, EPR. Right? So that's the EPR piece. Then you do a C0, goes down here, and then the H. Then there's a measurement gauge. And then you get classical information. You can do classical control of qubits using special commands. And overall, you would basically represent that entire circuit using that program. Now you can simulate it classically and look at various runs of that. And you can export it in various formats. So it's kind of neat to be able to do that. Of course, a full simulation, functional simulation, doesn't scale with a number of qubits. So if you want to do that for 1,000 qubits for a very generic operation, it won't work. If you know something about the operation, you can still handle thousands of qubits. So for instance, I've been doing some reversible computations. So yesterday we heard from Mike Mosca about reversible computations. They are nice because they're just commuting stuff around, right? You're just commuting basis states. So you can actually track that basis state as it gets commuted. You can track that, and it scales quite well. The largest one I have done was several thousands of qubits and several hundred thousands of gates for a reversible operation. But of course, as soon as you have stuff like Hadamard gates in your circuit, it splits kind of two paths. And if you have n of them, you get kind of 2 to the n paths in the worst case that you need to track, and then it doesn't scale so well anymore. Dave Wecker has implemented Shor's algorithm, for instance, using the method I mentioned briefly in part 1. That method uses only 2n plus 3 qubits. And basically it uses some controlled rotations in the circuit, and it uses the Fourier transform. You can see that here. And a few of these Fourier transforms back and forth, that's part of this method that goes back to Beauregard. And that works well. So Dave has done, I think the largest was some kind of 4-bit numbers that could be fully functionally simulated. You might say, what's the point? The point is just to see how far we could push that technology and how many bits we can handle. And there might be other algorithms on the small number of qubits that you want to check. Maybe to falsify some ideas. Maybe you have an idea for an algorithm and you want to make sure it works. And by looking at a small scale simulation, you could check. Right? And if there's an issue, then you can go back to the drawing board and make sure there's no problem. So I implemented Shor D-log, not the elliptic curve one, but the finite field one. So the abelian group is just a multiplicative group of a finite field. You pick one generator, like a primitive element, and you get another element of the finite field, and you want to solve the D-log problem. So for that, I've been doing it. It was also the instances, of course, are ridiculously small. I think the largest prime was some 4-bit prime that I could do using that method. I can show you. I have that on my laptop. I can show you how this code looks like and how you define gates and how you can simulate that algorithm. If you run it, then typically you just run it in a shell, at least that's what I do. And then you can output some kind of debugging information. So in that case, I ran, like I was working in GF17. I picked 3 as a primitive element, and I wanted to know the solution to the discrete log problem for 5. So 3 to what power is 5, not 17. Just as a proof of principle that this works. And I generate exactly that algorithm I showed you in the first part of the talk. You remember that kind of 2-register algorithm. So at the end of the day, you measure and you get 2 results out. So that whole bit vector here really decomposes into 2 parts. And you can interpret that again as an integer. So it turns out that in that algorithm, you don't always succeed. So you measure 2 registers, you get a pair x and alpha x, or ax. And you must have that x is a unit modulo p minus 1. Because the group has order p minus 1. It's really an additive group, cyclic group ordered p minus 1. If x is not a unit, then you cannot infer what this a or alpha here is, right? And you still would get some information about it, but you could not uniquely nail it down if it's not a unit. So I kind of give up in that case if I measure here a 0 divisor, and I can see it because the number is an even number. I read from right to left, small bits to larger bits. So you see it's an even number, and in that case, it just didn't work. In another run, so it's randomized, in another run, I pick a different number down here, and the number is 1, 1, 1, 1, so that's 15. Right? That's an odd number, so it's invertible mod 70, GF17 star, which is cyclic order 16, right? So any odd number is invertible there. You can compute the inverse of that number mod 16, take it times the other register, which in that case is 8 plus 2 plus 1 is 11, right? You get a certain value, which is 5, and then lo and behold, 3 to the 5 is equal to 5 mod 17. It's useful for this kind of experiments with small-scale algorithms, and they can be quite non-trivial because there can be some classical post-processing in the algorithm, and here there is sort of classic post-processing. It's kind of really nice if it eventually works out. It took me quite a while actually, because I made many mistakes when I had the circuit, and even getting one gate wrong usually ruins your entire quantum algorithm, right? And that happened to me a lot when I played around with it, but eventually it seems to work fine. And as I said, the largest primes, the largest size of the finite field I could handle were like 4 or 5 bits. So it's not that big, but at least like some non-trivial examples I could do. Okay, let's go back to theory, unless you have questions about that simulator part, about liquid. Any questions? Is it too easy or too difficult? Right. If there are no questions, I'm going to move on to, again, more theory. I will extend the period finding framework, basically in 2 ways. One I call the hidden shift, and one I call hidden subgroup problem. And unfortunately, it's going to get harder from here. So if you have questions, please use it to slow me down. Come on, guys, you must have some questions. Yeah, there's a question. That's a good question. The question is, so I mentioned that there's a noise model. The noise model is built in. Do we have a mixed state simulator, or is it a pure state simulator? Right now, my understanding is it's all pure state based. So you can start with a pure state, you get a run. There are certain noise models like depolarizing noise you can add, but it's not a full mixed state simulator. It doesn't simulate general channels, as far as I know. It does it based on pure states. I don't know, does that answer the question? I think it's a possible generalization would be to do arbitrary channels, and certainly interesting to do it, but I don't think they've done that yet. Okay, question back there?
It's a more general question, but so is there something like a universal quantum computer that takes a quantum program and compiles it and then spits out something which evaluates the quantum program, and or is a representation of the quantum program, and what is spitting out from this compiler?
That's an excellent question. If I understand correctly, you're asking whether this compiler is universal in some sense, that it could specify any target unitary. Is that what you're wondering about?
And also what is the outcome of this compiler? Is it a set of gates, or is it that it can be run?
Yeah, good question. So I think the question really is, what does this compile to? As we don't have it in architecture where we could run it on, what is it actually outputting, right? So I should start with before I describe the output, what the input is. So the input is a program specified in a high-level language. Think of C or Haskell or some high-level language where you can express. Essentially, you describe a circuit that you would like to implement, but you describe it in a concise way. You could, for instance, have a loop. You have maybe a for loop, or you have a primitive recursion to define the circuit. But then what happens is it will rewrite that program in several stages and eventually produce a list of gates, like a net list or like a logical list of gates, very much like an FPGA instruction set. Right, there you would have like a list of maybe table lookups or something. And here you would get a list of elementary gates, like T gates and C naughts and so on. But it's not yet mapped to a physical architecture. That's kind of an intermediate stage, right? I'm describing that now. From there you could then go lower level and replace each gate by an underlying fault-tolerant gate. And there's some support for that already there. But eventually the goal is to map it even to the physical layer where operations will be really controlled pulses and fields, and it depends very much, of course, on the actual physical quantum computer, what it is. It might be some kind of wave function that you need to actually then apply using microwave. Maybe you need to send that down to the chip. So that level is still for the future, but in principle it could be interfaced to that. So that would then be the ultimate assembler level, right? And the ultimate targeting will be of that level. What I described in the example I showed you was at a high level where I stopped basically at Clifford and T, like a universal logical gate set. But the idea is to have the full stack going at some point. Yeah. More questions? That's great. So I'm going to talk about another use case of the Fourier transform. In part one, we have seen the Fourier transform, we have seen the circuit, and we have seen that it's very efficient on a quantum computer. You can even think of it as being almost instantaneous. And it was very useful we saw one application, namely, it's useful to extract periods. And in a nutshell, what Cho's algorithm does is it sets up this state that's periodic, and there's a lot of value in learning the period. And if we know the period, we can suddenly factor. But the problem is that we don't know this offset. So the Fourier transform gets rid of the offset, it turns it into a complex phase. In the spectrum, everything gets just pointwise multiplied by the complex phase, and the peaks that were spaced out with R are now spaced out with 1 over R. So if we now measure one of these peaks, we learn exactly that value here. It's a multiple of 1 over R, and if we know the multiple of 1 over R, we can learn what is R. Okay, so that's basically the use case, roughly speaking. Namely, that we can forget information about a coset. Right? So you got this annoying coset information, you don't want to have it, and you can use the Fourier transform to get rid of that information. Okay? And there's several ramifications of that idea. People found out, so you can use it for factoring, then it's really this picture up here. If you do D-log, you got a two-dimensional version where instead of having this train of peaks, you get a line with a certain slope, and the Fourier transform will map it to a perpendicular line, right? You remember that picture from part one. But there are more generalizations. So for instance, Halpern has shown that you can use it to find units in a constant degree field extension. That was his first result in 2002. And that in turn you can use to solve Pell's equation, which is a Diophantine quadratic equation. Which is not believed to be efficiently solvable classically, but there is a quantum algorithm that solves it. And the idea is very similar to this idea, but there are certain twists to it because the function is not exactly periodic anymore. And but still, it turns out the Fourier transform will do the job. There are other variations on the problem that I will not get into, but I give you the pointers to the literature here. But like another idea would be, if the Fourier transform works so well, and everybody knows that it's extremely useful to correlate data. So if you have a set of data and you get sort of a template and you want to see whether the template matches the data, it's incredibly useful to be able to compute convolutions. Right? So if we were able to compute really large-scale convolutions, we could do all kinds of template matching tasks. And we could do it potentially on gigantic sets of data, because we have just seen this morning that we can handle a range of n data points at a cost of essentially log n, right? Maybe a square here. So we can compute Fourier transforms of really long vectors in really short time. So why can't we use the well-known trick that a convolution is obtained by computing a Fourier transform of both signals and then pointwise multiplying them and then doing an inverse Fourier transform? Why can't we do that in quantum computing, right? It seems like a no-brainer because Fourier transforms are so cheap. Inverse Fourier transforms are essentially the same as the Fourier transform, right? It's just it's the same up to a permutation. So what's the problem with that approach? Does anybody see what the problem is with this approach? Why can't we use this idea to compute a convolution of two vectors? Yeah, question?
No answer. Because if we do it, we get, well, this is a function with one output, the multiplication, and we get the other one and can't uncompute it. So we have the other, and then if we do the DFT on the multiplication back,
Right.
it will not. It will be entangled. I mean, it will not give us the right result because of the auxiliaries that are not clean.
If I understand you correctly, you see an issue with the fact that the function has kind of two inputs, an f and a g, and if you would do it, it would entangle the two with each other?
No, it has two. I mean, it's not an injection.
Right. That's true. That's one basic issue. It's not a bijection. It's not a. First of all, it's not a linear map even if you have f and g both as inputs, right? It's not a linear map. It's kind of bilinear, but it's not a linear map on the space of fg pairs. But you could fix that problem by just fixing one of the two inputs. Then it's certainly a linear map, right? It goes from f to just f convolution with g. That's a linear map. But you made exactly the right point. That map is not guaranteed to be injective, right? So it's not, and everything that we do on a quantum computer must be unitary. So if you take f to f convolution with a fixed reference function, it's linear but not guaranteed to be unitary. That's what I wanted to say really. Okay, and that's precisely the point, is that this pointwise multiplication here, right, is in general not a unitary operator. Just think of the extreme case where you would have a zero in the spectrum of G. In the Fourier spectrum, it might have well a zero frequency. Then you would have to perform a pointwise multiplication with zero, and that cannot be a unitary operator, right? Yes, but maybe there are some cases where it works. And indeed, there are some cases where this whole sequence of operations is unitary. Does anybody see when that happens? Yeah. Correct. So the answer was, it is unitary if this spectrum here, DFT of G, consists of just phases, right? Because if it's just phase, let's see if I can do that here. All right, okay, cool. Then I can do, I can compute the convolution of a vector. Let's call W DFT of f, right? Let's call it state f. And so let's call D the operator that's just the diagonal of all the Fourier coefficients of G. Okay? So it's a diagonal matrix that has here a G hat of 0 and so on. G hat of 2 to the n minus 1. Right? Of course we can apply this operator, right? Can map this state W, we can map it to D times W, right? And then this state really has coefficients that are f0 times G hat of 0, G hat of 2 to the n minus 1, f hat times G hat of 2 to the n minus 1. Okay? But of course that will only work if this operator here is unitary. And this works only if those numbers are all just complex phases. If one of them is less than 1 in absolute value, so if any of these G hat of I is strictly less than 1, that's not going to be unitary. But if they all are equal to 1, right, if they're all complex phases, then in principle we can do that. And that's actually a kind of nice perspective, because we could now ask for what functions G have that magic feature that the Fourier spectrum is exactly flat, perfectly flat, right? It needs to be perfectly flat. But if it is the case, then we can actually perform that convolution. So, and then the question is, do these functions exist that have a flat spectrum? And if so, can we do this, and is it useful? So that's where I want to go next. So I'm going to show you now a class of functions which is flat. So we can do this convolution algorithm for this class of functions. But let me first define a problem that's related to this, where this actually arises as kind of you have the need to do this convolution. And the problem is as follows. Suppose you have a group. This group here, let's think of it as being an abelian group, but it could be really any even a non-abelian group. You get two maps from that group to some root set, and you get the promise that the two functions just differ by an offset in the domain. Right? You're looking for that offset S. Let's actually assume it's abelian, and let's write it additively. So you know that on all x you kind of get this relation, that they're shifted versions of each other by this S. You don't know what S is, and you'd like to find out what S is. If you were just to query the function, you evaluate it at certain points, it might take a very long time to figure out what S is. Right? Because there might be many S that are consistent with evaluating the two functions. That's of course not an argument, but one can make that argument rigorous and show that a classical algorithm has a very hard time figuring out what the S is. In particular, if both F and G are sort of inside a black box. And an algorithm can only access it by querying the black box. In that scenario, we would actually prove that this problem takes exponential time, classically. But for some functions, it can be done very efficiently on a quantum computer. So the first function for which it could be done is the so-called Legendre symbol. It's the function that tells you whether an element of a finite field is a square or non-square, right? So it's a plus minus 1 valued function, or technically it has 3 values because 0 takes 0, but otherwise it just takes plus minus 1. And it was shown that if you take a Legendre symbol and you shift it, so the Legendre symbol looks something like this. You want mod p, and you want to know if a given element is a square or not. And if your function g is just a shifted version of this, right, then we get an instance of that problem. And I think there was indeed a proposal to use a shifted Legendre symbol as a pseudo-random generator. I think it was broken, or it was definitely not, as far as I know, but there was some time ago there was a proposal to build a generator using such shifted Legendre symbols. A quantum computer could extract the shift efficiently. And I show you the algorithm that will do that. The question is, why would we care? I mean, okay, Legendre symbol, nice, but are there other generalizations of this idea that would maybe give rise to different algorithms, or maybe help us attack some crypto systems? The honest answer is we don't know yet. There are more general classes, so this has been generalized to more broad classes of functions, and I'll show you some of those, but still it's not clear if that helps to attack crypto systems yet. There is some overlap between this hidden shift problem on the left and the hidden subgroup problem that I briefly touched in the morning, and I'm going to go a little bit in more detail later. There are several applications of the hidden subgroup problem. Factoring and discrete log we've already seen. Health equation is another, but it even relates to lattice problems and graph isomorphism. We don't know that about the hidden shift problem yet. So we don't have really nice killer applications for the hidden shift problem, but it's certainly a nice algebraic problem where there's hope that a quantum computer could outperform classical computers. Okay, so let's dig a little bit deeper into the algorithm to solve hidden shifts. So just from the get-go, you've got to realize that you cannot hope to solve hidden shift problems for any function. So there has to be something about the structure of the function. In particular, you've got to have something like a flatness condition. And indeed, it turns out if your function has a very non-flat spectrum, like if you take a delta function, and you compute the delta function now into the phase. Like in time domain, you have a delta function, so it basically has value 1 everywhere. Right? This is now value 1. And just there's one magic value where it drops to minus 1. Not doing a good job writing here. If your function looks like this. So your constant 1 is everywhere, and only once you drop to minus 1. And that happens at S. Then that will be a delta function. So the Fourier transform of this is very non-flat. It has a huge peak at 0, and then it has some phase information that encodes this S, but very far from being flat. So indeed, those functions are very bad for the hidden shift problem. It takes a very long time. Basically, it reduces then to the so-called search problem, for which there is an algorithm that's faster than classical, and we hear about that algorithm later this week from Stacy. But like basically you can get a scored speed up, but that's it. I mean, for these kind of delta functions, you cannot hope to be better, much better than a classical algorithm. However, there are functions like the Legendre symbol, here it is. Here you can do it with essentially one query to f, one query to g, and you're done. You find out what this s is. And that's kind of really surprising, and let me show you what the algorithm looks like. So you start by initializing a quantum register in 0. It's a set of qubits, they are initialized in 0. And then you create an equal superposition of all the states. That can be done, for instance, by applying Hadamard gates to all the qubits. That will create an all one vector, right? Because if you take the tensor product of all these little H2s, you get a matrix that has the all ones vector in the first column, right? Do this 10 times. You have that little guy, tensor itself n times. And it's very easy to convince yourself that that matrix looks like this. It has all ones in the first column, and then it has stuff here. And you don't really care about, because you're going to hit it with a vector that looks like this, 1, 0, 0, 0, 0, right? Which is the vector 0. And then you create a state that's really the flat superposition of everything. Okay. So that's one way you can think about that state. So that's the state we generate here. Now you evaluate the function g, which is the shifted version of f. You evaluate that in superposition and compute the function value into the phase out here. Okay, that can be done. Once you have an implementation of g, you can implement the function into the phase. There's a simple way to do it. Mike mentioned it yesterday briefly. It's called a phase kickback. If you want to look that up, for instance, in Nielsen-Chung, there's a very good description about how this phase kickback method works. But like the bottom line is, whenever you have a function that you implement like this, right? So suppose you have a circuit that does this, you can always turn it into a circuit that computes it into the phase like this. Okay. Vice versa, it's unfortunately not true, but you can, like this way it always works. But if you have a box that does this, you can use phase kickback to make this. So you do that, and you have the circuit for G, create this state, and then you just perform a Fourier transform. What the Fourier transform does is, well, you get now a spectrum, and mathematically you can write it down like this. It's the sum of all these frequency W, and you get you could basically, we should write it like this. Some Fourier coefficients for the function g, right? But then we have the knowledge that f is just a shifted version of g. So the spectra of f and g are related. Right, thank you. So in particular, we know that if you shift the function in time domain, you pick up this this linear factor, right? So we can write this state. We can rewrite it in this form, where we pull out the linear factor out of the spectrum out of the Fourier coefficient for f. But now we made the assumption that f had a flat spectrum, so we can apply this diagonal operator that we mentioned before and sort of get rid of this term. Now it looks like really nice, because now you have a state that looks like this, and that's just one of the basis states of the Hadamard basis. Right? So if you do another Fourier transform, you really literally get just S. And then if you measure, you get the classical information about S. So if you could do all these gates perfectly, there would even be an algorithm that would never give you a wrong result. It would be a zero-error quantum algorithm that starts from a classical state, does some quantum stuff here in the middle, but it ends also with a classical state. Okay? Still, we have no way of knowing how to simulate that method. It goes from classical to classical. It never errors. It always gives the right result. But it does some quantum magic in the middle, and it will extract this information about S. All right, so that was a nice paper by Wim van Dam, Sean Algren, and Lawrence Ebb. It was a solar paper. And kind of the question is, how do we generalize this, right? Can we, what are the steps that are critical? And obviously one step that's critical is the kind of the assumption that the function has a flat spectrum. Can we sort of work around that? And can we find other functions besides the Legendre symbol that have that property that the spectrum is flat? So let me show you one class where the spectrum is flat and where we can apply this. Those functions are defined on the hypercube, so not on the cyclic group, but on the kind of direct product of many Z2s. And those functions have the feature that all their Fourier coefficients are the same. They are not like complex phases, they're just plus minus 1 phases. Those functions are known to exist, provided that your overall dimension of the hypercube is even. So you gotta have that little n up here must be even, but as soon as you have that, then you find functions that have exactly that property to be spectrally flat. So if you look at those functions in time domain and frequency domain, they're both plus minus 1 valued. And then of course you can define another Boolean function. You start with a Boolean function here that's bent. You look at the Fourier transform as it's plus minus 1 again, it defines implicitly another Boolean function, which is sometimes called a dual. And one can show that it's again a bent function. So for any bent function you get a dual bent function, and if you do another Fourier transform you get back. So whenever you have a bent function, you can try to implement that algorithm as well. But the only catch is that you have to be able to do the diagonal operation, and it turns out the elements of that diagonal operator are exactly the values of the dual bend function. So in order to pull off that algorithm and make it work, you gotta have a way to implement the dual bend function efficiently. Okay, it's not always given, unfortunately, that's the case. I mean, as probably some of you know, bend functions are used, say, in the design of symmetric ciphers, or people try to be at least close to being bent. So they have some use in crypto, and also it's quite easy to find some bend functions, namely like a really useful family is just take the inner product and you have another degree of freedom, then you can commute the second input. So both inputs here are bit vectors, x and z are vectors in 2 to the m. You can scramble one of the two, say scramble y, by some arbitrary permutation. And this is not just a permutation that reorders the bits, it's really a permutation that reorders all bit strings. So it's an element of the symmetric group on 2 to the n symbols, right? So this is gigantic. So that is 1 out of 2 to the n factorial many permutation. You have that many choices. You can take any of them. You can even add another function that just depends on y. And all of these functions will be bent. In the dual bend function, you can even write down in a closed form what it is. It's basically the x and y change roles. You get the inverse of pi in x, and you also get g, and then you evaluate the inverse of that. It's very simple to prove that. It's just basically substitution for that variable, and then you can see that exactly that function pulls out. Those slides you'll get online very soon, so you can try to see how that proof works. So that gives us a lot of candidate functions for which we can do the same algorithm. And what the algorithm really looks like that I showed you before, if you write it as a circuit, it is a Hadamard transform followed by g, right? That was the shifted function. Hadamard transform, the dual bend function, Hadamard transform, and that's it. For those who know about optics, that's exactly like an optical correlation. In optics, you would have like a lens that does one. So that part here would just create an incoming wavefront. That's like a lens. Fourier transform, that's a phase element, like a phase plate, like a glass plate. It's like a phase plate. And that's again another lens. It's like an optical convolution. Only that we do it now in a quantum memory using the Hadamard transform. So the catch is really that the function you care about might not be flat. So there are tricks that you can do. A very simple trick is to just force it to be flat. Right? Of course, you can, if your function has a non-flat spectrum, you can just renormalize the spectrum by dividing the action coefficient by its absolute value. That will make it flat by force. Unfortunately, that might completely screw up your function because it might have had some very small Fourier coefficients, and if you do that, then it can even get unbounded, right? You would have a division of 0, that's not a good thing to do. But even if they're very close to 0, you would now you renormalize it by very much and distort the function very much. But there's a method, and it's called rejection sampling, in case you want to look that up, that does it in a very gentle way, and it does it in a way that can be proved to be the best possible. So if you have your actual spectrum, and you want to renormalize it in some gentle way, that's the kind of the optimal way, then there's a method that does that. It basically will create another qubit, rotate that qubit carefully, and then map the state back into the original space and implement that. It's more graceful than that brute force renormalization, but it's a method that allows you to apply the framework, the same framework here, for functions that are not completely bent. Okay, so I think I'm running out of time. I can show you, I also implemented some of these algorithms in Liquid. Just want to show you a small scale simulation. So after the first step, everything is completely flat. Then you compute the function g, and I'm showing now where it's plus and minus 1, it's a certain pattern. And then you do the, and actually that's a shifted one, and that was the unshifted one, right? The task is how to find that shift. So now if you Fourier transform, you again get a flat spectrum. It's really perfectly flat, it's just plus minus 1. If you now pointwise multiply with the dual band function, you get this pattern. If you now Fourier transform, you get exactly that one S that you're looking for. Right? It's supported on only one. And that's also easy to simulate, at least for small scale. You can prove an exponential separation in query complexity for that problem, but there's a kind of small fine print here. You gotta assume that both f and g are given by oracles. If one of the two is just known, is a fixed unknown function, the most you can show is a polynomial separation in query complexity. But if both are unknown, then you can play this game that if, so this is roughly speaking what the argument is. If you have a classical algorithm that makes a polynomial number of queries, say queries all the stuff in here, then still there are so many candidate S that would be consistent with exactly what that algorithm queried. So they could change it to a different S. That's a very well-known argument, and you can make that work even against probabilistic algorithms using the so-called Yao minimax principle. You can fight against a distribution over deterministic algorithms instead of arguing about probabilistic algorithms. So that way you can show that even a randomized algorithm cannot solve the hidden shift problem with bounded error, whereas a quantum computer, you can show it can do that. And kind of the family of bent functions that underlie that proof is just the Majorana and Farland class. Okay, do I have like a couple more minutes, or is that basically running out of time? All right, okay, let me come to it. Like, we just want to mention hidden subgroup because it's a really nice framework. And it generalizes, sure, for factoring and D-log. And people have tried to apply that framework to the dihedral groups. Of course, you all know what a dihedral group is. It has actual implications. Dihedral hidden subgroup problem has implications to lattice problems, in particular SVPs for certain types of lattices. And it's also related to subset sum problems. And Regev, building on these insights, has then later defined the LWE system. Of course, that's a different problem than, say, subset sum, but like the inspiration, I think, came from this earlier work. It's one of the crypto systems that I proposed as a post-quantum candidate, but we don't know really how to do it. And I think part of the motivation comes from the fact that we don't know how to tackle the dihedral hidden subgroup problem. If you want to go completely crazy in terms of non-abelianness, you can look at the entire permutation group, the symmetry group, and then you basically arrive at graph automorphism or graph isomorphism. The problems are related. There are reductions from graph isomorphism. If both graphs have no self-automorphisms, you can reduce it to graph automorphism. And graph automorphism has a very nice description as a hidden subgroup problem for Sn. I'm not going to go there, but I'll leave that in the slides in case you're interested. Just as a message, it turns out that it's very difficult to apply the hidden subgroup framework to graph automorphism. If you follow exactly these steps, it turns out you need a very big quantum computer to do it. So for Shor's algorithm, you only have to have one register at a time and work with that, and that's it. To do graph isomorphism, we know we must use at least n log n many registers. If our graph has n vertices, we must have that many registers. Each one has n qubits, and then we need to entangle them in some way that nobody knows how to do it. So that's a little bit depressing, but people even use that negative result to say we can turn it into something good by basically defining a one-way function. So Moore, Russell, and Vazirani some years ago proposed to a one-way function, so that finding collisions for that function, if you were able to do that, you would in particular be able to do graph automorphism. And because of that result I just mentioned, we know that a quantum computer would have to be quite large to tackle it. So that's an indication why that might be a quantum-resistant one-way function. There's still some questions open about that scheme. For instance, it's slightly expanding. That doesn't seem like very nice. Maybe that could be optimized in some way. And also, the question is really like, are there no better approaches to quantum, like no better quantum approaches to graph isomorphism than treating it in this hidden subgroup kind of way? Right? There might be better ways. So that's something interesting, and it's part of my list of open problems. So post-quantum, I couldn't get into it, unfortunately, but that's an area for active research, and I put some open problems here. It's even interesting to just implement some Fourier transforms for certain families of non-abelian groups. It's open as far as I know for some families, and I gave you some more modest literature, and I'm going to stop here. Thank you very much. More questions? Question, maybe we've done special guest.
So you mentioned that there is some connection of your problem to the Macalise crypto system, right? If you draw, that there's some similarity between Macalise and a lattice crypto system that encodes a crypto which is a little bit related but not the same.
Right.
So why is this related to to codes, and the other side, the hidden subgroup problem to lattices? Is there already some intuition behind it?
There is already, well, yes and no. There's already a result, again, by Moore and Russell and Din. Din was a student of Alex Russell. They showed a reduction of the Macalise problem. It's kind of a special version of the Macalise problem. You got no kind of one of the codes, and then it's a translated version of the Macalise. But that translates into a hidden shift problem over a certain non-abelian group. It's essentially like the linear or the affine group. So we don't know how to handle that, actually. So they use that to argue that Macalise is safe against certain types of attacks. So if it's again a Fourier sampling-based attack, they showed it's safe. If I remember correctly, they showed it's safe against like one copy at a time. So you do like Fourier sampling on one copy. Whereas to get the full power out of Fourier sampling, you would have to use several copies and then entangle them. So I'm not sure if they looked into that already, or if it's on the list of.
Boils down again to that you are in the non-abelian case. Yeah.
Yes,
Okay.
it's a non-abelian shift problem.
Okay.
Right.
Okay. Yeah.
But on the same level as the LWE reductions that are known, I don't think there's anything known about Macalise. Yeah.
Okay. Time for another short question. Okay. If not, let's thank the speaker again.